Assalamu alaikum and good evening, everyone. I would like to thank you all for coming to our webinar today, and I would like to welcome you all to our today's webinar, which is organized by IEEE Women in Engineering Affinity Group Student Branch, University of Dhaka. I am Marcia Zaman Shoili, lecturer of IEEE Department and the group advisor of IEEE WIE Student Branch, University of Dhaka. Today, our honorable speaker is Dr. Nafisa Noor ma'am, Assistant Professor, Electrical and Computer Engineering Department of North-South University. She has expertise on nanomaterial synthesis and various types of electrical, optical, and material characterization techniques and electron microscopy imaging tools. Her works include the phase change memory nano devices and zinc oxide nanomaterials. And today she will be sharing her expert opinion on nanoscale phase change memory devices. Now I would like to welcome Dr. Nafisa Noor ma'am, and I would like to request her to start the session. Dr. Nafisa Noor ma'am.
Thank you very much, Ms. Zaman. I'd like to first of all ask whether you can hear me well.
Yes, ma'am, we can hear you very well.
Okay, thank you for the feedback. My name is Dr. Nafisa Noor. I'm the assistant professor of North-South University, and today I'm going to actually show you a very general overview of the field of phase change memory nano devices. And this is one type of memory technology. So here we are going to learn about the memory technologies first of all, and then we will learn why we need the phase change memory. So for today's webinar, I have already pre-recorded 4 modules, and I'm going to stream those modules. So these modules are short, so I'm going to pause after every module and come back to the audience and take your questions. So that is how I'm going to keep today's discussion more interactive. So in between the videos, if you want me to ask any question, or if you want me to answer any question, then please let me know. You may interrupt, that is also fine. So I'm going to share my screen to start the first module, if that is fine. Is that fine, Ms. Zaman? Should I start sharing?
Yes, sure, Miss.
Okay. So just give me one moment. I'll just share one more time.
Sure.
Because I have to share my sound.
Yeah.
Okay, never mind. This time I made another mistake. Okay,
it's
never mind.
It's okay.
Okay, so let me share my screen too. Okay. All right, so let's start the first module. And here I would introduce the memory. So I'm going to stream the video, and let me know if you don't hear any sound. And if you hear the sound fine, then we can just continue. Assalamu alaikum, everyone. Good evening. Welcome to the webinar on nanoscale phase change memory devices. My name is Dr. Nafisa Noor. I'm an assistant professor at the Department of Electrical and Computer Engineering of North-South University, Dhaka. In today's talk, I'm going to present a general overview on the phase change memory nano devices. This presentation has been divided into 4 separate modules. After each module, I'll pause and take the questions from the audience. In the first module, we will introduce the semiconductor memory concepts. In the second one, we will compare between several existing and emerging memory technologies. In this module, we will also discuss about the importance of the new memory technologies like phase change memory or PCM. On the third module, we will introduce the concepts or fundamentals of phase change memory or PCM devices. On the fourth module, we will discuss about several reliability factors of the PCM nano devices. Welcome to the first module of today's presentation. In this module, we're going to introduce the concepts of the semiconductor memories. I'd like to start with some very general pictures of the global digital lives. Digital devices nowadays are becoming ubiquitous in our everyday life. Recent statistics of January 2020 shows that About 67% of the world's total population use mobile phones, and 59% of the world's population use internets. From another recent statistics, we see that more than half of the global internet users use mobile phones, whereas the rest use mostly laptops and desktop computers. Besides these mentioned percentages of the world population, there are also people who use the laptops and desktop computers offline. Hence, the computers and other smart electronic devices have become an inherent part of human civilization. Now, whenever we go to buy any electronic device, we carefully check the specifications. The most important two hardware components that we check are the processor and the memory specifications. Here is an example of a good laptop computer. The memory specification of this laptop is highlighted in the yellow color as 12 GB RAM, where RAM stands for Random Access Memory. In addition to this, there is also 1 terabyte hard drive storage facility. However, if we look into the specifications of the high-end and newer laptops, you may notice that the hard disk drive is partially or completely replaced by the new forms of storage devices such as the SSD and Optane. These specifications clearly indicate that the memory and storage technologies are progressing rapidly, and people's demand are also changing accordingly over time. In general, people want to afford faster and smaller devices with low cost, high capacity, and low power consumption. In order to fulfill this growing consumer demand, semiconductor industry has been improving the memory device technologies for many decades. Starting from the 1940s, various random access memory and read-only memory devices were discovered for different purposes. In order to understand their roles in a typical computer, let's take a look at the memory hierarchy of a computer device. We can organize the memories used in a computer in a few different levels based on the speed of the memories, their cost, and the capacity that we can use. So on the first level of this memory hierarchy of a computer, we have the CPU register. These registers are extremely fast and they are used only of a smaller quantity because of the extreme high cost. These memory units are within the processor. They process the data and the instructions. The values are stored temporarily here. In the next level, we have the cache memory. The cache memory consists of the static random access memory or SRAM devices. The SRAM devices are also as fast, almost as fast as the CPU registers, and they are also used of a small quantity but slightly larger capacity than the CPU registers. And their cost is also slightly less than the CPU registers. Now here we temporarily store the data that are most frequently used by the processor. In the next level, we have the main memory, which is comprised of the dynamic random access memory or DRAM devices. These devices are slightly slower than the other two levels, and they can also be used with larger quantity as compared to the cache memory. And here, the price is also slightly less as compared to the SRAM devices. Now, in the main memory, we store the data that the processor is currently working on. So these top three levels of the computer memory stores the data temporarily. And in terms of the cost, all of them are pretty high. And in terms of the speed as well, their speeds are quite similar. In the order of nanosecond, we have their write latency. So all these memory types are considered as very fast memory, and also at the same time we can call that they are very costly memories. Now on the other side of the computer memory hierarchy, we have the permanent storage area. This is also called as the secondary memory or the mass storage area. So this type of memory is significantly low in cost and their speed is tremendously low. So here you can compare the speed of the other memories that are in the nanosecond range, whereas in this case, the traditional hard disk drive has only 10 millisecond for the write latency, which is 6 orders of magnitude larger than the DRAM write latency. So because of the very low cost, we can also use this hard disk drive of very large quantity. But the very strong problem here is that these are tremendously slow as compared to the main memory, and there lies a speed gap between the temporary memories and the permanent storage facilities. Now, in the traditional computer, where the hard disk drive is used as the only storage facility, there will be almost 6 orders of magnitude difference between the writing latency between the memories and the storage facility. So, the memories have to wait very long to receive the information from the storage devices. So, this large gap can be bridged with the solid state drive, which is composed of the NAND flash technology. But here you may notice that the write latency is not super high for this NAND flash technology or these SSD devices as well. So we can only go up to maximum 2 orders of magnitude higher in the write latency, but there would still be a large gap between the storage and the memory devices, and the problem is not still solved. Hence, nowadays, many emerging technologies are evolving, including the phase change memory that have the properties in the middle of the memory and storage devices. So the features that we have for PCM or its other counterparts, these features are in the middle of the memory technologies and the storage technologies. And that is why they can smoothly bridge the gap between the memory and the storage technologies. Besides the speed, PCM and its counterpart technologies combine several advantages of these existing memory devices and several advantages of the existing storage devices. For example, if we look at the volatility nature of these memory and storage devices, we see that the memories such as SRAM and DRAM are volatile, which means that when the power is turned off, the information stored in these memories will be erased. On the other sides, we see that these storage devices are non-volatile, such as the SSD and the hard disk drive are non-volatile, and that is why they ensure the permanent storage even when the power is turned off. So PCM and its other counterpart technologies combine the good side, which is the non-volatile nature. Also, there is another important memory feature which is called the endurance. The endurance number indicates the number of cycles we can cycle a memory without deteriorating of its features. So by maintaining two states, we can cycle the SRAM and DRAM up to 10 to the power 16 times, which is a very large number. But on the other side, you can see that the SSD, the NAND flash technology, has a very low number for the endurance, which is only 10 to the power 5. So PCM and its counterparts have the endurance numbers that are in the middle of the memory and the storage technologies. So combining the good sides from the memory and the storage technologies, this PCM and other counterparts of it are bridging the speed gap, and also they are basically working as a storage class memory, which is just in the middle of the memory and the storage facilities. So in our next module, we're going to discuss more about these comparative analysis between different kinds of memory technologies. Thank you for your attention on this module.
Okay, so we just completed our first module, and I'd like to come back to the meeting room again to accept the questions from the audience. Is there any question? You can let me know if there is any question.
So yeah, I have one question.
Yes, please go ahead.
So this is Rumana Rahman, by the way. The name on the computer is different. It's my nephew's name. So yeah. So are there currently any models of the computer that are using PCM at this moment in the market?
Yes, in my next module, I'm going to show the commercial Intel Optane memory. So Intel has already packaged this Intel Optane. So I'm going to talk about that in the next module. So you can learn more about that.
Okay.
And also you will see that many other companies are currently working on it. And in the next module, I'm also going to talk about the counterparts of PCM. There are some other technologies that are also similar to PCM. They all are similar because they change their state by changing the resistance. So I'm going to talk about those, and you'll see that all the other counterparts technologies are also being researched rigorously, but PCM got the most technological maturity.
Thank you very much.
Welcome, thank you.
Assalamu alaikum.
Walaikum salam.
Can I speak in Bengali?
Yeah, that's fine.
Thank you. আমার একটা প্রশ্ন ছিল, সেটা হচ্ছে যে PCM এর স্পিডের ক্ষেত্রে slide it was about 100 nanoseconds, right?
Yes, yeah, that's what I wrote for the write latency, but when you read different papers, you will find slightly different values. The reason behind that is when we do the materials engineering or the cell designs, those modify these values slightly. Sometimes some materials can improve this latency, whereas those materials can probably deteriorate some other properties. So it's just from a reference that I have given here, but you may find slightly more or less values.
May I know what's the lower boundary of the speed limit?
In my next module, again, you will find around 20 nanosecond. That's what I have found so far, around 20 nanosecond.
Okay, thank you so much. Looking forward.
Okay, yeah, welcome. So when you see the next module, you will find that many of these parameters do have some boundaries, some upper and lower, and those are based on different materials and different cell designs. I got one question from the chat window. What is the main difference between SRAM or DRAM? It is just only a difference with time or another one like as element or cost or many sectors. So I'm really glad that you are already interested to know more about the SRAM and DRAM, and all those things you will find in detail in the next module. So you will see how the SRAM and DRAM look like. You'll know more about their properties, their advantages and disadvantages. And I also have shown the cell structure for the SRAM and DRAM as well in the next module. So Aryan Shubho, for your comment, I think I would refer to the next module. Any other question? Okay, so if we don't have any further questions, so I would think that it's a good time to move on to the next module, and probably we can gather a lot more interesting questions after we watch the next module. So again, I'm going to share my screen another time. Just give me one moment. All right, so let's watch the next module now.
Hello again. Welcome back to the second module on the webinar on nanoscale phase change memory devices. In this module, we're going to compare between various existing and emerging memory technologies. We have already learned about the existing memory technologies, and these are the SRAM and DRAM. The SRAM stands for the static random access memory, and DRAM stands for the dynamic random access memory. We learned that both of them are very fast, so their read and write latencies are in the order of nanosecond, where SRAM is even faster than the DRAM. We also learned that these two memory devices can be cycled up to a very large number, which is in the order of 10 to the power 16. So we can cycle up to this very large number without any deterioration of these cell states. Now here we are also learning a few other disadvantages of these memory cells. For example, if we focus on the SRAM, we see that it has a very large feature size, which is 140 F square. And if you look at this cell structure, you would see that there are 6 transistors in the SRAM cell. So that is very difficult to scale down. So that is a big disadvantage for the SRAM cells. Also, in the DRAM cell, we have a capacitor. And whenever we have a capacitor in the memory cell, that is also difficult to scale down. So the scaling of the SRAM and DRAM are quite difficult. On top of that, we already learned that both of them are volatile. And in addition to the volatility nature, which means that the power, whenever the power is turned off, the stored memory will be erased. On top of this problem, there is another problem in the DRAM, and that is it requires frequent refreshing because this capacitor discharges quickly and refreshing of this capacitor is required. Now, if we compare these properties of the SRAM and DRAM with another non-volatile current storage solution, which is the NAND flash, we see that here we have some good facilities, such as the NAND flash is non-volatile. So it's good because we can retain the stored data even when the power is turned off. We also see that this is much more scalable. Here the feature size is 5F square, and this is also easy to fabricate because the flash cell basically looks like a transistor with a floating gate. So it's much easier and low cost fabrication. But there are some significant disadvantages in the NAND flash technology. So the first one is that this is quite slow. The read and write latencies are in the micro and millisecond range. So again, there will be significant speed gap between the memory and the storage. So that is a problem. So the flash is not really, or the SSD is not really solving our existing problem of the speed gap. And another problem is that the endurance of the flash is significantly lower than the SRAM and DRAM. So this will not run for a long time. Now, if we check the properties of PCM and its counterparts, such as the STT-MRAM, which stands for the Spin Transfer Torque Magnetic Random Access Memory, and the RRAM, which stands for Resistive Random Access Memory, we see that these three technologies have quite similar features. All of them are non-volatile in nature, so they will retain the stored data even when the power is turned off. All of them have much smaller feature size. These feature sizes are much smaller than the SRAM feature size. Now you may see that there are some lower and upper bound for each of these cases. The reason behind that is sometimes these memories are used alone in a crossbar array, and sometimes they also accompany a selected device. So when there is a selected device like a diode or transistor to introduce the nonlinearity in the selection process, the feature size will be on the upper side. But if this device is used alone, then the feature size would be on the lower bound. Now, it's good to have lower feature size because we can increase the density, but the problem of using the device alone is that some of the neighboring cells are half selected or partially selected. So that is a problem because there will be some crosstalks between the cells, which is not also accepted. So there are several pros and cons in scaling of these devices, and engineers prefer the ones that are required. Now here we see that the read and write latencies are again in the nanosecond range, which is closer to the main memory or DRAM technology. And we also see that the endurance of some technologies are as high as SRAM and DRAM. For example, for the STT-MRAM, the endurance is really as high as the SRAM and DRAM. For the others, it's in the middle. It's not as low as the flash, but it's not as high as the SRAM and DRAM, rather they are in the middle. So based on all these features, combining all the speed and the endurance features, these technologies are used for different purposes. For example, the STT-MRAM has the potential to be the main memory, whereas the PCM and RRAM are still being considered as the storage class memory, which features as both the storage and the memory facilities. So with the improvement of the materials of the cells and the cell design structures, these properties can be further improved. And this is a currently ongoing research trend in these non-volatile emerging memory technologies. Now here we are looking at a glance all the pros and cons of these existing and the emerging technologies. So the red are the indications of the cons and the green colors are the indications of the pros. So we can compare that here we have mostly good size in PCM and its counterparts. Now here I have included another technology that has not been discussed in the previous slides. This is known as the FRAM, which is the ferroelectric random access memory. This is also considered as one of the counterparts of PCM, and this is also advancing almost at the similar space. And here we see that the advantages that we see for PCM and the other counterparts are also observed in this other technology. Now this is a graphical presentation of the write cycles and write latency of the existing and emerging memory technologies. And here we see that the NAND has the slowest writing time, and the PCM RAM has in the middle, whereas the SRAM and DRAM has the highest write time and also the highest write cycles, which is the endurance, and MRAM and the STT-MRAM fall in the very similar category as the SRAM and DRAM. And that is the reason why the STT-MRAM is also considered as the main memory, whereas the PCM and RAM are considered as the storage class memory. Here we can see the graphical presentation of the price and the speed. We see that the L1, L2, and L3 represent the level 1, level 2, and level 3 of the cache memory. And these are the most expensive and the fastest memories. Then we have the DRAM, which is slightly lower cost and also slightly slower. Then we have the PCM, which is represented by this 3D crosspoint, which we are going to introduce very soon. And then we have the SSD, which is the NAND flash technology, that is slightly lower price, but significantly slower. And then we have the hard disk drive. Now, this is a graphical representation of the market share of various existing and emerging memory technologies. From the data of 2019, you see that the largest portion of revenue was made by the DRAM and the flash technologies. And among the newer memory technologies, the PCM, RAM, and MRAM had the smallest revenue, which was only $0.5 billion, as compared to the $111 billion of the total revenue of 2019. Now, with an annual growth rate of approximately 9%, we see that in the forecast of 2025, the overall market revenue is expected to grow up to $185 billion. And again, the forecasted market would have the DRAM and flash as the major components. And we see that the PCM, RAM, and MRAM, the circle that you see in the maroon color, has the largest increase with an annual growth rate of 42%. So if you compare this individual growth rate with the other growth rates of the smaller circles or even the larger circle, you would see that the largest growth is expected in the next 6 years for these emerging non-volatile memory technologies. Now, this is a graphical representation of the manufacturers of the non-volatile emerging memory technologies. Light blue color, we represent the PCM, and we see that these manufacturing started from the year of 2004 with PCM, and the major manufacturers for PCM are the Samsung, ST Microelectronics, We also see Hitachi and Mnemonics. And we also see IBM. And here the size of this circle is representing the technology nodes. Now the data shown here is up to 2015. And in the next slide, we are going to see some recent data. In the recent years, we see that PCM, which is represented again with the blue color, we see that Micron and Intel are producing the PCM devices in the recent days. The memory used in the Intel Optane is the 3D crosspoint, which is the phase change memory, and it is expected to bridge the gap between the existing memory and the storage technologies. This 3D crosspoint memory has a phase change material in series with a selected device, which you can see here in these ACM images. Now, in this module, we learned about the comparative analysis between various existing and the emerging memory technologies. And we find that the phase change memory is the one that can bridge the speed gap between the existing memory and the storage technologies. So in our next module, we're going to learn more about the phase change memory fundamentals. Thank you for your attention on this module.
Okay, we are again back to the classroom. No, the meeting room, sorry. Never mind. It's just a habitual practice to say the classroom. So I'd like to take the questions from the audience again on this second module. Is there any question from the audience?
Miss, can I speak in Bangla?
Yes, sure. Please feel comfortable.
Miss, I have a question between DRAM and SRAM. And first of all, আপনি যখন একটা ডিফেক্টর দেখাইছিলেন যে that means এটা ডিফারেন্স mean between হচ্ছে ক্যাপাসিটরের মধ্যে DRAM and SRAM এর মধ্যে আপনার ফার্স্ট যে ওইটা ছিল। এখন আমরা যদি অন্য কোনো একটা মেনু কোনো একটা ট্রাই করি যে লাইক আমরা SRAM এর মধ্যে এই ক্যাপাসিটর ইউজ করার মতন, দেন এটা কি সম্পূর্ণ কি এটাকে আরো ডেভেলপ করা যাবে SRAM and DRAM এর চেয়েও? কোনো কিছু যেটা ল্যাগিং স্পিড বলেন, এরপর রাইটিং স্কিল বলেন, সবকিছু মানে ইনক্রিজড থাকবে?
Okay, it's a very interesting question because you are probably thinking about finding new type of memory technology. So I would say that first of all, it's SRAM. SRAM stands for static random access memory and DRAM stands for dynamic random access memory. So I would say that the way SRAM works with the 6 transistors, if I show you one more time, let me just share the screen one more time on the, yeah. So if you see here one more time, the way these transistors are arranged is basically, it's the 4 transistors that you see here in the middle are basically 2 back-to-back inverters. So when we connect these inverters in this way, whenever we power it up, there is a predetermined state that we get, because when you connect 2 inverters in this state, they would always give you a specific value, either 1 or 0. So when you have a very large array like this with many SRAMs, then you would see that there are some specific values during the power up. Now, there are also ways to measure these values with distance amplifiers. Now, on the other side, the way the DRAM works, it has a capacitor and a transistor. So the way they work are different. And if you think about some creative way to combine them, then I would say that if you come to this chart a little further, you would see that some of the newer memories do have some combinations of those. Say, for example, here, the cell elements that I have listed for different memory technologies, you may see that some of them again have the features. For example, the FRAM also has 1 transistor and 1 capacitor, but the capacitor work in different way. It's like a ferroelectric capacitor. Now, what you are trying to say is that can we combine the features of SRAM and DRAM together? Then I would say that we could, but first of all, we don't want to get the cons that you see here. So first of all, the SRAM has 6 transistors, so it has a very large feature size. So if you think about some new memory, then we would try to get one that doesn't have the problems that are highlighted as the red here. So we don't want to get a large memory structure. That's why we'll not try to get so many transistors or the back-to-back connected inverter. Also, having the capacitor is a problem. That's what I have already mentioned, because if you have a capacitor, it is really difficult to scale it down. And that is why you may see that this FRAM also has a capacitor, and its lower and upper bounds of the feature size is way too larger than the other counterparts that you see in this list. So we don't want to have a capacitor in the memory cell, and we don't want to have too many transistors in the memory cell. So the better ones that we have nowadays basically have either just a resistor, and here by the resistor, the R, we mean the cell itself. Say, for example, in the phase change material, when you apply different pulses, the resistance of this phase change material would change. That's why with the R, we represent the cell itself, or the material included in the cell itself. So the cell resistance itself is the R. So these are easy to scale down. That's why we want to combine the good properties, but we just don't want to combine the ones that that are highlighted as red here. Does that answer your question?
Yes, miss.
Okay, I got another question. Would you please explain the function of a selector? Yes, that's a very interesting question. So we can use these devices with or without selectors. Now, imagine that we have a very large array. In the array, we need to access a particular device. Think about a 10 by 10 array where we have 100 devices. So we want to select a particular one. Say, for example, the one that has the coordinate of 4, 5, okay? Say the vertical position is in the 4th and the horizontal is on the 5th position. So we want to select that one. We want to either read that or we want to write that. So when we want to select a cell very precisely, we need to include some sort of non-linearity in the selection process. So first of all, we do have some biasing schemes. We bias those vertical and horizontal wires that are connected to that specific cell. But when we want to select it, the other cells that are connected on the same vertical or the horizontal wires also get half selected because of the biasing schemes we use. Now, if we use some selector like a diode, then those diodes will make sure that only the selected cell, I mean the diode that is in series with the selected cell is in the forward bias, and all other diodes connected with the other cells are either unbiased or reverse biased. So by doing that, we can only flow the current through the desired cell. Now, we can add this diode in series with our devices, but that will increase our area, because one resistor plus one diode, or like one resistor plus one transistor would cause a lot of area per memory cell. So it increases the area of the cell or the feature size. So what you can alternatively do, you can use the memory itself. But if you want to use the memory cell alone with no other selector, then your memory cell should have some sort of non-linearity. There should be some non-linear IV characteristics in that memory cell so that you can operate the cell in such a way so that you apply a certain current and only your desired cell gets selected. The other ones get either half or partially selected. So that's basically the function of the selector. Does that answer your question, Dr. Mohammad Kubur-Zaman? Does not the selector make the circuit complex? I would say that the selector would not make the circuit complex. Rather, I would say that those are better. I mean, the only problem is that they make your cells feature size larger. But when you have the diodes or the transistor as the selector in series with your memory cell for each of the junction, that is even better because you can precisely select one cell, and then there will not be any other cells that are have selected. So you can precisely write on a specific cell. So your other cells will not be written unwanted in an unwanted fashion. Okay, thank you. Any other question? All right, so if we don't get any question, then it's a good time for us to move on to the next module. And we hope to get even more interesting questions after we finish the next module. So let me again share the screen.
Hello again. Welcome to the third module of the webinar on nanoscale phase change memory devices. In this module, we're going to discuss about the fundamentals of the phase change memory or PCM nano devices. We have already learned that PCM is an emerging computer memory technology. PCM is fast, dense, and non-volatile. And we already learned from our previous module that the meaning of non-volatility for the memory is that the information stored in the memory will be retained even when the power is turned off. Now, there are various cell designs reported for this memory device, and the most common feature is that there is a phase change material placed between two electrodes. The cell design that you see here is known as a mushroom cell. And in this case, the phase change material is shown as the blue colored region. And here, the blue colored region has one type of state, and the red color region has the other type of state. Now here, the two electrodes are arranged in the vertical position. That's why one is known as the top electrode, another is known as the bottom electrode. In many of the cell designs, we have such top and bottom electrodes, but in some lateral cells, the two electrodes are arranged in the lateral fashion. Now, in these cells, we always would have some phase change material, as you see, as the light blue color. The most common phase change material is the germanium antimony telluride, which is also known as the GST. And the common composition for that is the 225 composition. The resistance of the phase change material can be switched between the different resistance levels when appropriate electrical pulses are applied. The high resistance state is called the amorphous or HRS, and the low resistance state is called the crystalline or LRS. To switch from the low to high resistance state or to amorphize this cell, we need to apply a very high amplitude electric pulse, which is also known as the reset pulse. The reset pulse would have such an amplitude so that a small portion of the material is melted. So the temperature at this portion of the material has to exceed the melting temperature of the GST material. And then we also end this pulse with a very sharp fall time. During this sharp fall time, the molten material is cools down or quenched abruptly. So this leaves a disordered state in this smaller active region of this material, and that disordered state is known as the amorphous phase. And because of the disorder of that state, we have the HRS in this material. Here we can see this schematic representation of the disordered amorphous state. Here, the different colored circles represent the different atoms included in the germanium antimony telluride material. Now, when we want to go from the high resistance state to the low resistance state, or when we want to set the cell, we apply a set pulse. And in this set electrical pulse, we have a lower amplitude as compared to the reset pulse. Also, in the set pulse, we have a longer fall time, and during this fall time, the disordered atoms in the amorphous state get enough time to get into its ordered structure in the crystalline structure. Now, in the crystalline state, we have low resistance because of this ordered crystalline lattice. Now, one thing to notice here is that during the set pulse, the phase change material does not have to melt, but the material temperature should exceed a level temperature that is known as the crystallization temperature. Now, at any state, when we want to read a cell, we apply a low voltage read pulse or a low voltage DC sweep. We apply low voltage so that there is no disturb in any state of the cell, so that we do not program further during the reading of the cells. Now, depending on the size of the cell, the high resistance state can be in the order of 10 to the power 7 to 8 ohm, which is like 10 mega ohm to 100 mega ohm. And the low state can be in the order of 10 to the power 2 to 3 ohm, which is in the order of kilo ohm or less than that. Now, the LRS also has two states. One is known as the hexagonal closed packed, which is obtained by annealing the cell for a Celsius. This HCP state is not obtained by electrical pulsing. Only by annealing at this temperature or by heating at this temperature, we can obtain this state. The other state at the LRS is known as FCC, which has slightly higher resistance than the HCP state. At the FCC phase, we can obtain the FCC phase by annealing at the 180 degrees Celsius. This FCC phase can also be obtained with the means of electrical pulsing. Now, because of this very large memory window between the high resistance state and the low resistance state, the PCM, HRS and LRS can not only be easily distinguished from each other, but also we can accommodate various other program states in between the HR LRS. These intermediate states can have resistance levels that are in between the LRS and HRS levels, and these intermediate states are also known as the mixed states. In these mixed states, we have these cells in various proportions of the amorphous and crystalline states. Now, these different phases in this cell can be located differently, so we also observe significant variability in these mixed states. Now, when we program PCM cells into many cells like this with some intermediate states, we call such operation as the multi-level cell or MLC operation. In the MLC operation, we have more than 2 levels. So say, for example, if we have 4 levels of operation, these 4 levels should have distinguishable resistances corresponding to each of their states. And when we have 4 levels of memory operation, we also call it as a 2-bit memory operation. In our last module, which is module 4, we're going to learn a lot more about the MLC cell operation and the other reliability factors related to the PCM cell operations. But before we conclude the current module, we're going to learn about how to fabricate and how to characterize the PCM cells. So here we are showing an example of the germanium antimony telluride 225 line cells. And here you can see the SCM image or the scanning electron microscope image of these line cells. Here you like the dog bone shape, and the GST material lies in the middle of 2 laterally placed electrodes. So here the right side of the electrode is here and the left electrode is here. So instead of the top and bottom electrode, in the lateral arrangement we have the left and right electrodes. And in the middle we have the GST material. So you see this dog bone shape because the middle width of this cell is the active region in this cell, and this is extremely thin. So when we want to make this cell extremely thin, we have to go toward this dog bone shape. but we can also get a rectangular shape, but that rectangular shape would not have such extreme small width in the middle. Now the process steps would include a lot of the setups. For example, we have to grow the oxide first, and we have to open the trench, then we have to deposit the metal, which you see here as the blue. We have to polish the metal, and then as the red we are representing the GST film deposition. Then we pattern the GST film, and finally we cap the top part with silicon nitride. So the line cells that you see here are 50 nanometer thick, and they are on silicon dioxide. They have bottom metal contacts, and they are capped by silicon nitride. Now you may wonder whether these are nano devices or not. The answer would be yes, they are nano devices. Why? You may wonder that their length is over 100 nanometer, and by definition any device is called nano device if their dimension is below 100 nanometer. So the answer why this is nano device is that we call a device nano device when the device has a sub 100 nanometer dimension in any of its dimension, either length or width or thickness. So these devices are already 50 nanometer thick, which is already in the nanoscale regime. That's why these are already nano devices. So no matter what width and length we take for these devices, all of them would be nano devices because of the nanoscale thickness. These devices are fabricated in the clean room facilities where there are certain standards for cleanliness, and the users also have to wear the gowns for the clean room. These devices can be imaged with the electron microscope. Because these are in the nanoscale range, we cannot see them under the optical microscope. So one way to see them is under the scanning electron microscope image, and this is how a SEM imaging tool looks like. And this is an example of the SEM image. But sometimes we want to know further about the cell. For example, in the SEM image, we cannot really tell the difference between different materials or different states. So we often do advanced imaging, which is also another type of electron microscope imaging. And this is known as the transmission electron microscope or TEM image. Under the SEM image, we cannot distinguish the different phases of the GST material. But when we go to the TEM imaging, we can distinguish different materials and different phases of the GST material. Now, this is how the electrical characterization setup looks like. This is a specialized characterization setup, which is known as the cryogenic probe station. In this station, there is a chamber where we can go up to various temperature and pressure ranges, and we can take a look at the measured region with the help of an optical microscope and a monitor. And this is how a room temperature probe station looks like. Here also we have optical microscopes, several lenses, and we also have monitor to look at the area. But in this case, we do not enclose, or we do not really change the temperature. Rather, all the measurements are done at the atmospheric pressure and the room temperature. Now, when we want to apply programming pulses to these devices, either we can apply a single pulse or we can apply pulse trends. Pulse trends are often applied to go to the intermediate states more precisely. And we're going to discuss about more details about those MLC operation in our next module. So thank you very much for your attention on this module.
Okay, we are back to the meeting room again. And now I'd like to take the questions from the audience. The students can ask the questions in Bangla if you feel comfortable as well. So I've prepared these three modules for anybody, I would say, for students of any level. But I would say that my last module is made for the faculty members or the graduate students, or I could say that the fourth year students. You may find yourself a little overwhelmed at the fourth module if you are a very young student, but I still encourage you to watch that. Okay, so I got one question. How do you consider the defects, if any, in the crystal? So that is an interesting question. So if you want to characterize that, then we would do some extra diffraction characterization techniques to tell more about the crystal itself. And was that a characterization related question, or what was your specific question? I would like to also inform you that sometimes when we anneal the cells, we often see some voids as well in those cells. So the voids can be seen under the SEM images if the voids are pretty large. And a very interesting thing is that in the crystalline cells, even if we anneal all cells at the same temperature, the temperatures were shown in my videos. So even if we anneal all cells of similar dimension to up to the same cell you have just presented, is it the microtensed PCM cell architecture? Actually, no, this is not a microtensed PCM cell. This is called a line cell. The line cells are very basic lateral cells. So these lateral cells would have one right and a left electrode, and the cell would be just laterally placed. So these are some very early type of cell designs, and these are pretty good for the research purpose. These are not used in the like in the commercialization purpose. They do have some drawbacks, but those are pretty good for the characterization and research purpose. So those are called line cells. If you want to find some other synonyms, then I would say you can call them lines or bridges or wires, but those are not microtensed PCM cells. Yes, somebody probably want to ask a question.
Madam, আসসালামু আলাইকুম। আমি যেটা কোশ্চেন করেছিলাম যে ডিভাইসের যে আগে যদি ফ্যাব্রিকেশন করা হয়, ক্যারেক্টারাইজেশন সেটা হচ্ছে ডিভাইস ফ্যাব্রিকেশনের আগে যে ক্রিস্টালিনের যে ডিফেক্টটা, আরেকটা হচ্ছে যে ডিভাইস ফ্যাব্রিকেশনের পর যদি মানে ডিফেক্টটা মানে ধরেন যে কিভাবে আমরা ওটা কনসিডার করতে পারি, বা আমরা ধরে নিলাম যে হয়তো কোনো ডিফেক্ট নাই, বাট তারপরেও যদি মানে ডিফেক্ট থাকে বা যে কোনো ধরনের ডিফেক্ট, সেটা ভয়েড হোক বা ইমপিউরিটিজ হোক, জাস্ট সেটা আর কি আমি কোশ্চেন করেছিলাম।
Okay, so I would say that during the fabrication, a lot of characterizations are done, and also after the fabrication, like when we complete the annealing steps, several characterizations can be done. But you know that these extra diffraction kind of things are done on thin film, not on the device level. So the only characterization that we can do is the electrical characterization, optical characterization on the devices, because these devices are very small.
Okay, madam, thank you very much.
Okay, any other question? Okay, so since I see no more question, then I would encourage you to also watch the last module. I would say that in the last module, I would talk more about the reliability factors. Now, up to this point, when you learn about the basic of PCM, you may go to many different directions based on your research interest. So I would go toward the reliability side because that is more relevant to my own research work. And you would find that most of the reliability that I'm talking about are related to the electrical characterizations, because I did the electrical characterization during my PhD. So I would encourage all of you to watch the last module, and I'd be really happy to see if some students also ask questions, because I could understand that the students are following up to the third or fourth modules. Okay, so let me share the video again.
Hello again. Welcome to the last module of the webinar on nanoscale phase change memory devices. In this module, we're going to discuss about several reliability factors of the PCM devices. We have already discussed about the high resistance state, the low resistance state, and the intermediate states of PCM. And we have also discussed the electrical pulses that are used for resetting and setting the pulse. Now, how do we get the intermediate states? In order to achieve the intermediate states, sometimes we may need to start from the LRS and we may gradually reset the cell so that we can stop somewhere at the intermediate states. Say, for example, if we start from the 10 to the power 3 or 1 kilo ohm, and if we want to go up to 10 to the power 5, or which is 100 kilo ohm, then instead of applying one single high amplitude reset pulse, we can apply some gradually increasing smaller reset pulses so that that can increase the resistance gradually. And as soon as we reach up to our desired resistance level, we can stop pulsing. So that is one popular way to go to the intermediate states from the LRS. But we often start from the HRS toward the intermediate states. So when we go from the HRS toward the intermediate states, we often apply smaller partial set pulses. So the idea is again the same. Instead of applying one large set pulse, we apply several smaller set pulses to gradually set the high resistance state toward the intermediate state. So pulsing in this nature is called partial resetting or partial setting of the cells, and we can reach toward these intermediate states from LRS or from HRS. Now the problem is that doing these partial set or partial reset operations can be tricky, because in these programming there are some variability in the reached programmed state. The obtained programmed state is often different than the target programmed state. So our program resistance can be different than the target program resistance, and these variations can be obtained from cell to cell. Say, for example, if this is an array where we have various cells, we may see that in order to reach to the same target resistance of 100 kilo ohm, when we start from the same initial resistance of 1 kilo ohm, and even if we apply the same sets of gradually increasing partial reset pulses, we may see that different cells are reaching to slightly different intermediate states. They are not all of 100 kilo ohm. So this is called the programming variability. And when we have this programming variability from cell to cell, we call this as the cell to cell programming variations. Now, when we have these cell to cell programming variations, we not only obtain this because of the process variations, where because of the process related steps, the sizes of these cells can be slightly different, which may require different pulses to reach to the different sets of pulses to reach to the equal resistance level. But on top of the process variation, we also have inherent programming variability in the PCM programming operations. So these programming variability is a physical source of variations which is unrelated to the process variation. So when we melt a cell and amorphize, this melting and quenching process itself has some variations inherent to it. Similarly, when we crystallize a cell from HRS to LRS, this crystallization includes the nucleation of small crystalline islands and their growths. So there are variations in the location of this popping up of the crystalline islands, and there is also variations in their growth. Hence, these amorphization and crystalline, both programming has its inherent physical variation, which we are terming here as the programming variability, which is an added term to the process variation. Now, because of this physical variation, we also observe this programming variability from the cycle to cycle operation on the same cell. So when we go from LRS to HRS, again come back to LRS, while going back to HRS again, we may see that in the 2 cycles of operation, we are not reaching to the exact same HRS. Also, we are not reaching to the exact same LRS, even though we are applying the same set or reset pulses. So these are termed as the programming variability. And in usual memory operations, we try to minimize these variations as much as we can. Now there is another problem in the multi-level cell operations, that is the phase change memory experiences drift of resistance, which is spontaneous and thermally activated. And this drift of resistance is mostly and severely experienced in the amorphous phase. Now the intermediate states also experience to some extent of this resistance drift, but the amorphous phase experience it to the most. The HCP phase does not experience any resistance drift, and the FCC experience very slight of it. But in the amorphous phase, we have the power law behavior, and we also can define some drift exponent to define how much drift we observe. Now, this is a thermally activated process, so as we increase the temperature, this drift can be modified. Now, this is an example of how the data retention is observed at various temperature of the PCM cell. So these measurements were done at various ambient temperature. The top black one was done at the room temperature, where you see that the amorphous resistance is increasing with the parallel behavior, and after reaching to a maximum, it would start decreasing. So this increase of the resistance is known as the resistance drift, which is an upward change of resistance. And again, I would remind you from the previous slide, we said that this is a spontaneous process and a thermally activated process. But this going down nature of this resistance is known as the crystallization process. Now, these can be modified when we go to higher ambient temperature. So at the room temperature, we can go up to 10 years of retention time in the PCM. So the retention time is defined in this way: how long it takes for the cell to retain the stored data. So when we store this cell as the high resistance state, we want this cell to stay at this high resistance state for a long time. So that is called the retention time. But this cell spontaneously is going to a much higher resistance and then going back to a lower resistance spontaneously, even at room temperature. So it takes about 10 years. So the retention time of PCM is about 10 years. Now, depending on the different material, this can be modified as well. And also when we go to higher temperature, the retention time can be in the order of seconds, as you can see here. Now the drift exponent that we define is a marker of how steep the resistance drift would be. For the HCP, we see almost no resistance drift. That is why the HCP crystalline phase is also known as the stable crystalline state. In the FCC state, we have very slight resistance drift, which is upward. And in the amorphous phase, we see quite severe resistance drift, which is also in the upward direction. Now, the data loss trend from the amorphous to the crystalline is would not always follow the same path. So if we cycle the same cell again and again, starting from the same resistance value, and if we anneal to accelerate the data loss process within a few thousandths of second, we would see that this data loss does not follow the exact same path. So the reason behind that is when we have these crystallizations in the amorphous region, there are some crystalline islands that would nucleated, and after these nucleations, these nucleated crystalline islands would grow in size. For example, here you see that one island is growing, and as other islands are popping up, they are all growing together and merging together. Now, this nucleation of different islands can be at different locations and at different times, even when we cycle the same cell during the crystallization of the different cycles. So because of these variations in their locations and the timing of their popping up, we can have different decrease of resistance for over time, and that is why we have different trajectory for the spontaneous data loss trend in the PCM. Now again, we are bringing back the drift exponent. The drift exponent can be slightly lower for the intermediate states. And if we consider the intermediate states, we would see that the higher intermediate states would have larger drift exponent, and the lower resistance intermediate states would have lower drift exponents. So we can explain that in the higher resistance intermediate states, we can have a larger proportion of the amorphous phase, and hence we see the larger drift exponents. And in the smaller or lower resistance intermediate states, we can observe smaller drift exponent because of the smaller proportion of the amorphous phase. I'd like to conclude this module with some key points. First of all, phase change memory, or PCM, is a fast, dense, non-volatile memory technology. Most commonly used phase change material is the germanium antimony telluride with the 2-to-5 composition. The resistance of the phase change material can be switched to the high and low resistance states with appropriate electrical pulses that are called reset and set pulses. And the PCM is a storage class memory which can bridge the speed gap between the existing memory and storage technologies. I'd like to thank you for your attention in all my modules. Finally, I'd like to acknowledge my institution, North-South University, for supporting me. I'd also like to thank University of Connecticut of USA, from where I did my master's and PhD. My works were done in the Nanoelectronics Laboratory of UConn, and the devices that you saw in this presentation were fabricated at the IBM T.J. Watson Research Center. These works are funded by the U.S. Air Force Office of Scientific Research and the National Science Foundation. Finally, I'd like to thank the IEEE Women in Engineering of the Dhaka University section, and I'd like to thank you for your kind attention on all my modules. If you are interested for my other publications, please check my Google Scholar profile. Thank you very much.
All right, so we are again back to the meeting room, and I'd like to take the questions on my last module. So before I get my questions, I'd quickly like to see the audience here. I couldn't get a chance to look at the audience. Okay. Is there any question from anybody? You may either type or you may ask. Okay, so I got one question. Would you please explain the slide number 5 and last slide before summary again? Okay, Dr. Mohammad Kubrizaman, thanks for your question. So, okay, so slide number 5, let me go back to slide number 5 first and share with you. Okay, so I'm sharing again the screen so that you can follow my discussion. All right, so here, what we show is that when we measure at room temperature, the data loss would be much slower than when we measure at higher temperature. Because in PCM, if we increase the temperature, the data loss becomes accelerated. Say, for example, at room temperature, we have 10 years of data retention. So at 10 years, if you program a cell at amorphous, first it will spontaneously go up and then reach to a maximum and then spontaneously will go down. So the upward transition is known as the upward resistance drift, and the downward transition is known as the crystallization. This happens spontaneously, and if you increase the temperature, then this transition would be accelerated. Now, if you go to slightly higher temperature, for example, if you go to hold on, for some reason I cannot find my, okay, I found my cursor. Can you see my cursor, by the way? here?
Yes, madam. Yes, we
okay,
can.
Okay, that's great. Now, if you look at this one, the 350 Kelvin, you would see that in this case, you would have a very similar transition of going upward, and then it would again go downward. Now, you may wonder why I don't have the data for the following. You may look at the author's name, Farooq Dirisalik. So the reason why they don't have the data afterwards is that if you look at the time scale, which is more than 10 to the power 7 second, it's already more than years. So they measure for years of this cell. So at room temperature in real time, it's really impossible to keep measuring the cell for 10 years. So it's expected to go down to its crystalline value, like FCC crystalline value, in about 10 years. And for the other ones, this transition of going from its programmed amorphous value to the FCC crystalline value would take shorter time. So if you go to 400 Kelvin, you can see that it would go in about like 10 to the power 6 times. So just by measuring for a few days, I should be able to crystallize it at 400 Kelvin. If you go to even higher temperature, then you can have this transition within seconds. So this transition is accelerated at high temperature. Now, you may ask then, how can we use this in the applications of like automotive and maybe in the industrial applications where high temperatures are involved. So the idea is that up to 120 degrees Celsius, the PCM can tolerate the temperature, this transition. It has a thermal stability. So 120 degrees Celsius is marked as the higher bar for a safe temperature zone. But above that, you would see acceleration of the data loss. So that is the explanation of this slide 5. Is there any other question on this slide? Dr. Kobiruzaman?
Madam, actually, in the device, if the temperature is increased after the 300 or 400 or 500, then its retention becomes lower, right?
Right. That's right. Yeah. You see that the retention time is lowering.
Yeah. So I'm not sure about the memory devices. Just I would like to know, for example, if the computer for a long time and heated. So is there any effect?
As I said, that up to 120 degrees Celsius, you are good. So 120 degrees Celsius is a lot of temperature. So it can withstand up to 120 degrees Celsius. So for your computer, it should be fine. But now, if you want to put it in an oven, then no, it's not fine.
Okay, madam. Yeah. Thank you.
Okay. All right. So your next question was on the on this slide. So this is a very interesting thing, and here you would see that the PCM has a serious limitation, or any type of resistive switching memory has this limitation in the MLC operation. So MLC operation is the multi-level cell operation. When you operate them with these many levels that are too close by, what can happen is that if the resistance is drifting over time, then you can see that the cells, these bits will be mixed after a certain time. For example, if you look at this time, you can see that between the blue and the pink, the threshold is here, and that's how you are going to distinguish these two states. But if you keep the same static threshold after a certain time, the resistance has already increased in the blue. So right now, the blue is no longer in its defined state. So you would see that the levels are mixed after a certain time if there is resistance drift in any kind of resistive switching memory. So that becomes a problem. So if you look at these graphs, you will see that here, the resistances are plotted in the x-axis has the logarithm of resistance. So at the initial time, they had a very nice distinguishing behavior. Their distribution of these resistances were like this. But after a certain time, when you have seen that they have drifted, then you would see that this distribution of this state is so much broadened that in some of the cases, there will be confusions about whether this is the 1-0 state or whether this is the 1-1 state. So there will be state mixing, which is a serious problem for the memories. So there are many types of remedies that are usually used for preventing this problem. Does that answer your question?
Yeah, madam. Yeah. Thank you very much. So just I would comment, because there are many students here. Yeah, and this type of memory devices can be simulated by console. So if any students or anybody interested, then they can use the different simulation software to simulate this type of devices. Thank you very much, madam, for your nice explanation.
Thank you. And at the comment box, at the chat box, I have shared one YouTube playlist link. If you go to that link, you can find the 4 modules that I have presented today. So if somebody is interested, they can, he or she can take a look at the modules later.
ম্যাম চ্যাট বক্সে অ্যাকচুয়ালি ওই লিংকটা আমার কাছে জাস্ট প্রাইভেটলি এসেছে, ওটা এভরিওয়ান দিয়ে।
Okay, so I would appreciate it if you kindly share it with other students.
Okay, sure. Okay, thank you, ma'am, so much. Thank you so much for making some time for us out of your very busy schedule. And thank you for your very informative and very interactive session. We have a few faculty members as well.
Sorry for interruption. There is another question.
Sure, go ahead.
Yes, please, Dr. Mohammad Kabir Zaman, please go ahead.
In the chat box, madam, other student maybe he asked.
Oh, yeah, Mohammed Aminul Haq. So should I take the question now? Do we have time to take the question?
Sure, ma'am.
Okay. What is the source of the resistance drift that you discussed? If we think at material level, in case of 450 Kelvin temperature, spontaneously some electrons are jumping from conduction band to valence band, and thus the resistance is going up. This phenomenon is really interesting. Can you please send some light on that? Okay, that is really an excellent question. So I like the way the student was trying to imagine the underlying physical mechanism. I believe he's a student. So it's really excellent. Actually, this is not the, there is actually a debate about what the physical mechanism of this resistance drift is. And just like you, many people have similar explanations regarding the electrons. But right now in this community, the most established explanation is that the structural relaxation of the amorphous, the disordered amorphous state results in this resistance drift. So think about a wrinkled paper. When you wrinkle a paper, and if you just keep it like this, it would slowly relax to its like a less disordered shape. So it's more like that. When you have the disordered amorphous state, it's like a super disordered state. So it would the structure would try to slowly relax and come back to its regular ordered state. So that's what you can explain. But again, there are many explanations, but this one is the most established explanation behind the resistance drift.
Okay, thank you, ma'am. It's a bit counterintuitive, as it seems that the entropy is going backward. Like, we know that ordered systems actually tend to go disordered, but in that case, it's the opposite, right?
I would say that the amorphous is more like an insulator. So the typical conductions in the amorphous phase or any insulator is different. So you need different types of transport equations to explain what is happening in the amorphous state. So there are some theories that describe these like structural relaxation processes, and you would find some papers that are back like 1 decade ago. There was a lot of work on the resistance drift, and you would find explanations of this structural relaxation. But in the community now, this is very rigidly established. This theory is now rigidly established as the underlying mechanism for resistance drift.
Yeah, I get it. Thank you so much.
Welcome. Excellent question, by the way.
Yes, we have a few faculty members with us as well. We have Dr. Mainul Hussain sir with us. I would like to request Mainul sir to say something for us.
Okay, thank you, Shweli, and many thanks to Dr. Nafisa Noor madam for her wonderful talk. I guess PCM is a very interesting topic, as we have seen today, and I myself have learned a few things and hope the students did too. So I'm a little disappointed with the number of participants. I was expecting more students to show up, but I don't know what happened. But I guess they can watch the recorded lectures later on and then learn about this. And one thing that I mean, the students, I should tell them that they can, I mean, it might seem complex initially when we see such a complex system like PCMs, but as you, I mean, go deeper into the concepts, you learn the basics, and then it becomes very interesting. And as Dr. Kabir pointed out, I mean, it's not only about fabrication, but you can also actually do exciting simulation work and get those published as well. So I would highly request the students, I mean, I can see mostly the volunteers are here, but they can go back, talk to their friends. They can watch the videos later on and then get back to Nafisa madam if they have any questions. So thank you everybody, and thanks to the organizers, the Women in Engineering. So with that, maybe I guess we can conclude today's seminar. And thank you again, Nafisa madam.
Thank you very much, sir. Yes. Thank you, ma'am.
Thank you very much for inviting.
Thank you. We are honored to invite you. And thank you everyone for joining our today's webinar. And with this, we would like to conclude our today's webinar. Thanks a lot, everyone. Stay healthy. Assalamu alaikum.
Assalamu alaikum.